We must now proceed to a new simulation involving water and splashes. The end result is visible here. As with any new simulation, we must first prepare our scene by removing anything unnecessary, particularly other simulations. In this case, we can also delete anything that isn't visible in our camera, such as the spaceship itself, debris, rocks, and so on. We only have the glass sphere explosion left, but no smoke or fire simulation. We only need the pieces that fall to the ground. Also, keep in mind that we used a keyframe sequence to transform this rigid body animation. This also allows us to reposition all of the animation in the timeline. Select all of the keyframes for each piece, and place them at the start of the timeline. The next step will be to fine-tune the animation of the pieces, so that they fall exactly as we want. Furthermore, we will only create the liquid simulation for one of the 4 pools. For the rest, we'll just make a water material. Let's start with a simple circular shape. Open the shading panel and make a material similar to this. This is a glass shader in essence. We must change the index of refraction to 1.333, which is the correct value for water. We can eventually change the value of roughness to make the surface more or less reflective. Then I added a volume absorption node. As the name implies, it simulates light absorption in the volume. We can also change its color to achieve results like these. However, we do not require a completely flat surface. The water surface must be rippled. To accomplish this, I'll add a bump node, which creates the illusion of an uneven surface, based on a gray scale map. And this map was made with a noise texture similar to this. To get finer details, we can change the scale, detail, and roughness parameters here. When we connect this map to the bump node, the grayscale values are converted into an optical reflection of the light, creating the illusion of a real noisy surface. So, connect the bump node to the shader's normal input, and this is the result. We must now adjust the way the pieces fall. This is how the rigid body simulations fall behaved. However, we need them to fall precisely into the pool, in order to have a good-looking water and splashes simulation. For example, this piece falls exactly on the pool's edge. And we have the option of moving it, or breaking it after the impact. And here is another example of how the pieces do not interact with the pool's border. Well, we could do it by hand. Or, using the pole, create another rigid body simulation of these pieces. You should already be able to do so. And you could do it as an exercise. I'd like to highlight only one issue that may occur in some cases when we perform a new rigid body simulation in a scene where we previously performed another one and then removed it. Some objects may exhibit unusual behavior. In this case, you should restart the simulation. And you can do so by clicking on this button in the Rigid Body World tab. This clears out all previous calculations. When we add a new rigid body object, Blender creates a new rigid body world setting for us. Okay, now I'll show you how I did it. consider the following. It is now animated using this keyframe sequence. So the first thing we need to do is remove the first set of keyframes. The pool must then be converted into a rigid body object. But, as soon as I do that, it appears to vanish. It was relocated to a new location. I wanted to show this as an example of the problem I mentioned earlier. So I reset the rigid body simulation, and it now works properly. Now, open the dope sheet and delete all keyframes after the location where you want the rigid body simulation to drive the piece. Then, give the piece a rigid body simulation and make it active. On the other hand, you must set the pool to passive. We also have to deal with the animated property, as we saw in the first lesson. Essentially, it must be animated using the keyframes in the first part. So, at the end of the keyframe sequence, we'll activate this property and add a new keyframe. In the following frame, we disable this property and add a new keyframe. As a result, from now on, the object will not be manually animated, but will instead be subjected to the rigid body simulation. And, as you can see, the object is now interacting with the pool. We must also ensure that the ground is designated as a passive rigid body object. But then something strange happens. Inside the pool, the object does not move. It appears that the object will remain at the top of the pool. This is because the pool's collision shape is set to convex hull. This means that Blender treats the object as if it were concave, with no holes. This is the quickest method for computing collisions, and it works in the vast majority of cases. However, in this case, we must change the collision shape to mesh. This allowed Blender to consider the actual shape of the object when calculating collisions. And now it works fine. Well, now consider this object. It collides with the border. Assume we want it to fall inside the pool or in a different location. We can't just select the keyframes and move them. The position of the entire animation must be offset. And we can do that in the graph editor. Choose all keyframes along the x-axis. Translate the curve upwards or downwards by pressing the G button. This creates an offset for the entire length of the animation. Do the same thing for the y-axis. And now we must repeat the procedure. We have to maintain the keyframes in the first part, and then add a rigid body simulation. Make an attempt to do it yourself. And here's what I got. Of course, we can now tweak the simulation parameters like friction, mass, bouncing, and so on, to get the exact result we want. Well, we can now move on to the water simulation. Before I continue, I'd like to mention something that could happen. This is the file we were working on before. If I scroll through the timeline, it appears that these pieces end exactly where the keyframe animation ended. As previously stated, this is regularly due to the fact that, when running a simulation, we must always begin and play the timeline from the beginning. And everything works perfectly in this case. This is one of the reasons why it is preferable to transform the simulation in a keyframe sequence, as we have done previously. Obviously, only after you're happy with the simulation. So, let's go back to the last keyframe where we disabled the animated property. Again, before baking, ensure that the simulation has been completely computed. To do so, go to the first frame and start playing the timeline. Well, select the Bake to Keyframes action and enter the required range. The simulation is now a keyframe sequence. So, every time we open this file, we know we'll get the right animation. Furthermore, this allows us to make minor adjustments to the piece's position. For example, we could move or rotate it slightly to get it exactly where we want it. Now we have to repeat the process for the second object. And here is the end result. I also made this animation of an object colliding with the pool's border and breaking apart. Finally, we can look at the water simulation. We'll get a short explanation of how this simulation works. The good news is that the fluid simulation and the smoke simulation share some concepts and properties. Well, consider this object. I'll also hide anything we don't need. As we did for the smoke simulation, we have to add a domain, and also a fluid source. So, I'm going to create an emitter, with the same shape and volume of the pool. I made it a little higher than the pool. This is because, as we'll see later, we need enough liquid to create splashes when the falling objects collide with the pool. We can extend the volume downward a little, because this portion won't be visible. Now, as usual, we have to add the domain. Increase its size so that it can hold the entire simulation. It's also a good idea to set its visibility to wireframe, so we can see what's inside. Consider that we want the splashes to be included in the domain. As a result, it must be sufficiently high. Finally, don't forget to apply the scale. Well, now we must convert these objects in the simulation components. Select the box, assign the fluid simulation, and set the domain type to liquid. Because the domain is also converted in the solid view, let's change its visibility back to wireframe. Now, select the source and set it to flow. And set liquid as flow type. The flow behavior has to be set as geometry. We don't want the fluid to be continuously emitted, unlike smoke.
It must only include what is contained within the pool's volume.
We can also see a preliminary result. To see the simulation below, you must first hide the liquid source object. The volume is completely filled with particles. When we begin the simulation, each particle behaves like a real object, under the influence of gravity. And the particles collide with the domain. A fluid simulation is thus based on the computation of each of these particles' movement. And each particle has properties that can be changed to produce different results. The more particles there are, the more realistic the simulation. And, as we saw with the smoke, the resolution division defines the simulation's final resolution, which in this case is proportional to the number of particles. Now we must design the water container, which has to interact with the water particles, to prevent them from flowing outside. I don't use the original pool object directly, because, as we've seen, it has to be higher. Furthermore, having a separate object for a liquid container, and the object that acts as the real collider, is always a good idea. This allows us to manage its properties, size, and so on separately. As a result, I'm going to duplicate the pool. I need to make it bigger. Change to Edit mode, and reposition the bottom vertices. Now we must convert this object into a real container, to prevent particles from escaping. To accomplish this, select the mesh, and convert it to a fluid object. However, you must select Effector in this case. And the collision option is enabled by default. This means that the object is now acting as a collision object, allowing liquid particles to collide with it. Let us see how it goes. Reset the simulation and play the timeline. However, the particles continue to flow outside of the container. Before we get to that, let's think about something else that might be useful in other situations. As you can see, the particles bounce back when they hit the domain. This can be avoided by turning off the border collisions property. We can only keep the bottom border. As a result, if some particles escape the container, they will vanish when they reach the domain boundaries. We must, however, investigate why the particles do not collide with the container object. The reason for this is related to the simulation's resolution, which is represented by this cube. The resolution is important because it affects not only the simulation's details, but also how Blender calculates the simulation itself. When Blender has to compute the collision of two objects, it must first detect the border of these objects. However, it can only detect borders if the resolution is high enough. Take a look at this box. The resolution of the simulation is represented by the size of the voxel. This is also the lowest resolution at which Blender can see the scene's objects. However, the container's border is smaller than this box. This is another way of saying that Blender cannot see it. So, the first solution is to increase the resolution divisions. The voxel is now smaller than the border. As a result, Blender can correctly detect and account for the border. This increases the number of particles as well.
If we restart the simulation, everything appears to be fine.
Because the particles can properly interact with the collision object, they are confined within the pool.
But there is another solution to this problem. And this can be used when we don't want to increase the global resolution.
Keep in mind that increasing the resolution also increases the computation time. We can simply add some thickness to the collision object's borders to make them larger than the resolution size. We can do the same thing with the surface thickness property. This increases the container's virtual size, as if the object were actually thicker.
This is the original simulation, with the particles flowing out of the container. Let's try again with a thickness of 0.5.
The particles collide with the container as expected.
Excellent work! We now have a liquid in the pool.
We also see how the simulation resolution affects not only the visual quality and details of the simulation, but also how Blender perceives and computes the simulation. Consider, however, that for the final simulation, as we did in the case of smoke and fire, we will need to increase the resolution in any case. And the resolution divisions could range between 256 and 512.
We'll look at the most important liquid properties here.
This section is essentially the same as saw for smoke. Also, in this case, I generally reduce the time scale factor slightly. Furthermore, in the presence of fast-moving fluids, we can increase the maximum and minimum time steps. The sampling substeps property is also present in the fluid source. And now we have some properties that are unique to liquid simulations.
The three main components that define the liquid simulation are shown here.
We have the liquid component, which is related to liquid particles. As previously stated, these particles are the foundation of fluid simulation.
As real particles, they move and collide. They define the fluid's movement and behavior as a whole. However, we need to render a fluid rather than the particles. This is accomplished by the mesh component.
This results in the creation of an envelope around the particles that represents the liquid itself.
Finally, there's the particles element.
This does not refer to the liquid particles we saw earlier, but to the spray, foam, and bubbles that a fluid, such as water, can produce.
These are optional components that can be enabled if necessary. Let's take a look from the top.
So, in the liquid section, we can specify exactly how these particles must be generated.
As a first option, we can select our preferred algorithm.
Flip is the most common, and is used the majority of the time.
The APIC one generates more stable simulations.
This means that it produces fewer particles that move too quickly, or exhibit unpredictable behavior. Flip works best for large-scale simulations. For instance, oceans, lakes, or any simulation involving a large fluid object.
And APIC for small-scale simulations, such as a tank, glass, and so on.
However, we can fine-tune this further by selecting Flip and then adjusting the flip ratio parameter. Essentially, we can define the flip behavior's strength. The simulation will be more chaotic and energetic as this value increases. The number of particles generated is determined by all other properties. A system maximum of 0 allows Blender to decide how many particles to create, based on the following parameters. Otherwise, we can precisely specify the number of particles we require. The particle radius defines each particle's virtual size. It defines its virtual volume, which influences how the particle interacts with the others. We can generally leave the other properties at their default values. I won't go into detail about these properties, because we already covered them in the liquid simulation course here on the platform.
I'll only mention the randomness property.
It is useful to distribute the particles unevenly. This has the potential to disrupt the particles' uniform pattern. Finally, consider that Blender automatically computes the number of particles based on the global division subdivisions we defined. As previously stated, this parameter increases the number of particles, adds more details, and allows Blender to compute the interactions more precisely. As a result, we only need to fine-tune these values when we need to achieve specific results, or something goes wrong with the simulation.
The following step is to make the actual liquid mesh.